So I want to talk to you about the arc length and the TNB, the tangent vector, normal vector, and binormal vector frame for a curve. Arc length is important. All this is important to what's called differential geometry, which is the basis for all astrophysics and physics, a lot of physics having to do with particle physics and physics of paths and things like that. So it's essentially what Einstein used to develop his theory of relativity. So it's pretty much all over the place. And it's very important. So the first thing I want to talk about is arc length. So we have this formula from Cal 2. If you haven't seen this before, it says the length of an arc of a vector function, and we'll call the vector function r of t, is from A to B, it's the integral of the length of r prime of t dt from A to B. So essentially what we've got going on here is we're going to have a curve in space given by a vector function, and draw this a little better. Curve in space given by a vector function. So basically we have little vectors going out to everywhere that are forming it. The endpoints of these vectors are the points of the curve, and the tangent vectors are defined everywhere. Okay, so tangent vectors have a certain length to them. All right, sometimes they're short and sometimes they're long. And so to find the arc length between any 2 points on the curve, let's call this point here R of A, and this point here R of B. So A and B come from T, all right? So our parameter is T. So for example, if you had something like R of T is T squared 1 over T. Okay, so then T comes from the real line. We're just going to pick numbers on the real line. And there's an A and then there's a B in there. And then that is mapped to our vector space. So a bunch of vectors. And these vectors form the space curve, one of which I have drawn up there. Okay, so you pick a number in the real plane, like 1. Let's not do 1, let's say 2. So you do 2, comma 4, comma 1/2. And then that will be a vector, and the endpoint of that vector will land on the graph. Okay, so each one of those points has a tangent vector associated to it. And so what I'm interested in doing is finding the length of the curve between 2 values, A and B. Now, the length of the tangent vector is the r prime of t with these brackets around it. So this is the length of a tangent vector. And so it seems logical to add up all the tangent vector lengths to find the length of a curve. And so that's what we're doing here. All right. So this is a formula I'd like you to memorize. So a little more detailed version of that formula would be the following. We know that if r of t, so let's suppose r of t is given by some x of t, y of t, and then z of t. So you can just think in your head like a t squared, 1 over t, something like that, or maybe there's signs in here or something, sines and cosines. Okay, if r of t is this, then the length of r of t is going to be the square root of all of those quantities squared. So length of r of t is x of t squared plus y of t squared. Let's draw it like this. Y of t squared plus z of t squared. Now, if you have the derivative of r, then its length will just be all these derivatives squared. So y prime of t quantity squared plus z prime of t quantity squared. And so that will give you the length of your arc. It's going to give you the length of your arc. And so this is another way to write it. You can write dx dt if you want, all those things. Okay, so what I want to do is I want to do an example of this that's going to run through this the whole lecture. And this is going to be a helix. All right, so let me draw this somewhere else. So let's find, well, I'm using purple, the length of the helix. And here the helix is going to be given by r of t equals cos t, sine t, and then t from, let's see what they say, t is what? T goes from 0 to 2 pi. All right, so 0 to 2 pi. From 0 to 2 pi. All right, so remember the helix just looks like this. So if you look, when t is 0, it starts at 1, 0, 1, 0, 0, and it goes up like this. And the helix lies on the cylinder x squared plus y. This helix lies on the cylinder x squared plus y squared is 1. Oops, that goes the wrong way. This needs to go the other way. Anyway, that goes that way. All right, so let's find the length of the helix from 0 to 2 pi. Now, remember, helix is just a circle that as soon as you start drawing it, you go up rather than around. You just start drawing it up. So you're picking your pencil up off of the plate, off of the paper, sorry, as you go up. So it's not like drawing a circle. It's drawing a circle, but as you draw it, you're going up with it. Now, what tells you that? Well, the t value does. So as t increases, the z value increases. So with a regular old circle, it would be cosine t, sine t, 0, and that will give you your good old friend, the unit circle. But with this helix, you have this t value, and so it's going up as you draw. All right, so let's go ahead and find the length by taking the derivative. So we have r prime of t is negative sine of t cosine t, and then 1. Now let's find the length of this. R prime of t length is, let's see, we're going to take the square root of negative sine t quantity squared plus cosine t quantity squared plus 1. Get rid of some of this. All this. And so sine squared plus cosine squared is 1, so we get square root of 2. Okay, so now what we do is go back to what the definition is. Go back to this here. So we found r prime of t. What's this? That's the square root of 2. And now we go from 0 to 2 pi. So we go integral 0 to 2 pi of square root of 2 dt. And so that's square root of 2t from 0 to 2 pi, which is 2 pi square root of 2. So apparently, the length of the arc from 0 to 2 pi of a helix is 2 pi root 2. So 2 pi root 2 is length of helix of radius 1 from 0 to 2 pi. Now, if we had just a circle of radius 1, then the area, the circumference, so the circumference or the arc length would be 2 pi r, or in other words, 2 pi. because r would be 1 here. R is 1. R is 1 we know in this helix because the coefficient of sine and cosine is 1. Where do we have it? Here we go. It's 1 here. 1. If it's 2, then the radius is 2. So what does it say? So apparently when we draw the circle, but we're picking up our pen as we go in the z direction, we pick up an extra square root of 2 in length from that. So if you draw a circle all the way around radius 1, you're drawing 2 pi units from the start to the finish. When you do the same thing, but you're picking your pencil up, then the start to finish is 2 pi times the square root of 2. Now, let's talk about what's called the arc length function. This is kind of like what you did in Cal 1, perhaps. It's a fundamental theorem of calculus part 1. That's what it was called there. So S of t is a to t of r of u du. Now what I'm doing is I want to keep t as my variable, but my limits of integration contain a t. So I've got to change my variable. So instead of r of t, integral r of t dt, I'm changing the variable to u, because we can't have the same variable that we're integrating against as we have as a limit of integration. Okay, so here's my arc length function. What this says is that this gives the arc length as t changes. So what does that mean? Well, if you take your helix example again, so we're going to draw the helix up. So what this gives here, S of t, is going to tell you the arc length as we go from one point to another. So if this is A and this is t, then S of t will give this length here. This will be S of t. That'll give that length there. Now, t changes though, right? So from A to like pi, and then A to 2 pi, and then A to 3 pi, 6 pi, and A to 8 pi, and A to whatever, 0, whatever A. You can even start at 0 if you want. So this will give you the arc length function. So let's do an example of this. Oh, I'm sorry. This is r prime with absolute values there. Let me show you. Let's back up here. Let's erase all this. So it's this right here. So essentially, it's just your good old, it's length of your vector, your tangent vector. It's the length of the tangent vector from A to T. All right, length of the tangent vector from A to T. So you're adding all the tangent vectors up. All right, so what does that mean? Well, yeah, definitely. Sorry, I didn't put them, but I should have. This is the length of r prime of u. So let's give an example of this. So for example, suppose we have r of t is the same one we've dealt with: cosine t, sine t, and then t. This is our helix again. Now I'm going to change it to u. So r of u is cosine of u, sine of u, and then u. So when we take the derivative, I'm just going to do the exact same stuff I did before. Sine of u, cosine of u, and then 1. And now the length of r prime of u is just the square root of sine squared plus cosine squared plus 1, which is square root of 1 plus 1, which is square root of 2. So what we get out of this is, so therefore, S of t is integral r prime of u, length of that, from 0, to go from 0 to 2 pi. Du, we found square root of 2 out of that. It's integral 0 to 2 pi, square root of 2 du. Now, when you do the math here, well, no, let's do t, actually. Let's do t. That's the arc length function. And then I'll do 2 pi in a second. So when you do the math, it's going to be square root of 2 u, because the integral of du is u, from 0 to t, which then gives square root of 2 times t minus 0, which gives square root of 2t. So the arc length function is s of t equals square root of 2t for this helix. So what this gives is, for every t value, s of t gives the length of the curve until then, of the curve up to that value. Assuming you start at 0, we're starting at 0. Start it somewhere else, then it's different. All right, so question for you. So question. When t equals 2 pi, so and does the helix going all the way around, what is the arc length? Well, all I have to do is plug it in, right? So what is the arc length? So what I'm going to do is I'm going to take this and I'm going to plug in 2 pi. So square root of 2 times 2 pi, which is just 2 pi square root of 2. All right, and so that's the arc length at 2 pi. Well, that's what we found before, right? So when we did this problem before, we found that when t was 2 pi, the arc length was 2 pi root 2. And there you have it. So, for example, so another example would be, or a question, when t is 1, what is the arc length? Length of RT. Well, it's just S of 1 is, I'm using my formula here. S of 1 is root 2 times 1, which is root 2. So at 1 radian, so at 1 radian, the length of the helix is root 2. So essentially, when you have r of t as sine t, oops, I think cosine came first. Cosine t, sine t, and then t, the arc length, s of 1, is going to be, so time out, 1 radian, so r of 1 is cosine of 1, sine of 1, sine of 1, and then 1. These are radians, okay, radians. So cosine of 1 is, I think it's 0.54. Yeah, so at 0.54, sine of 1 is 0.84, and then 1. So at this point on the helix, the arc length is root 2. Okay, so with that said, we can reparameterize it in terms of arc length. So reparameterizing. So what this means is that we're using a different parameter to parameterize our curve with respect to arc length. And I'll show you the advantage here in a second. Okay, so far we have s equals root 2 times t, which implies that t is s over root 2. So what I can do is I can say, well, r of t was cosine t, sine t, and then t, and everything was working great. But if I reparameterize with respect to arc length, then I take this s over root 2 and I plug it in for every t. So it'd be cosine of s over root 2, sine of s over root 2, and then s over root 2. And what this gives us is a way to parameterize the curve along the arc length instead of time, or I'm sorry, instead of angles. So we parameterize, we reparameterize. So let me tell you what, let me write it a different way. So note R of t is the parameterization. We just parameterization. Let me just write it out in terms of angles. Angle t, but R of s is the parameterization. Let me just say parameterization in terms of arc length. Arc length s. So what does that say? Well, basically it says, you give me an arc length, you give me an arc length, and I'll tell you where you're at on the curve. So given a particular arc length s, R of s yields the vector whose endpoint corresponds to that length along the curve. So what does that mean? Well, let me give you an example of this. So a really quick example would be, so R, well, let's just be writing down. So R of 2 pi root 2 would be cosine of, so let's bring this, what I'm doing is I'm using this. So it'd be cosine of 2 pi root 2 over root 2, and then sine of 2 pi root 2 over root 2, and then 2 pi root 2 over root 2. So this is the parameterization in terms of arc length, and we're looking at what point will we be 2 pi root 2 along the curve. Well, the root 2's all cancel, right? And so we're left with cosine of 2 pi. Let me write this in green. Cosine of 2 pi, sine of 2 pi, and then 2 pi. In other words, 1, 0, and then 2 pi. Well, that's just exactly where we were before. 1, 0, 2 pi is, let's see if I drew it. I think I did. No, I didn't. So let's see where that's at. So when you draw your helix, when you draw it, then when you go up around, so you're going around the circle basically, 2 pi, so now you're right above the originating piece, so you've gone around the circle once, then that is at, so remember the radius is 1, so this the bottom point is 1, 0, 0, and now this top point is 1, 0, 2 pi, which makes sense because you go out 1, over 0, and then up 2 pi. So the length of the curve along that is 2 pi root 2. So from here to here, the length is 2 pi root 2, and that's what this is saying. Where along the curve do we end up when the arc length is 2 pi root 2? Remember, R is parameterized in terms of arc length at this point. Arc length. Okay, not angles. Angles would be different. Angles is this one. Okay, so that's for parameterizing with respect to arc length, which isn't always easy because it's not, see, let me just point out something. It was real easy to solve for t here. This is your arc length function. For any t value, this gives you your arc length. And it was really easy to solve for t here, but it's not always easy. I mean, for example, if s is t squared minus 2t minus 5. Okay, this is not factorable, so solving for t is kind of hard. So you have to use Pythagorean theorem, all that stuff, and it's just kind of a pain. Well, not kind of a pain, it is a pain. All right, so everything that I've written here is essentially in the book, just explaining it different. Go over what smooth means. It just means when r prime is not 0, so we're only looking at smooth curves. We're not looking at curves that have some sort of kink in them. Okay, we're not looking at these. And if we are, we're looking at them piecewise. So it'll be piece A and then piece B. All right, we'll talk about that. Unit tangent vector, went over that last time. If you don't remember, it's just the vector divided by its length. So all these little vectors here are, let me blow this out, but all these little vectors here are unit vectors. Okay, and then the curvature. So the curvature is going to measure how fast the curve is changing with respect to arc length. So let me take this, let me pull it out and put it in a different part of the, video. So what I've done here is I've moved some of those formulas around. So the curvature is basically how fast the tangent vector is changing with respect to arc length. So it measures how fast t is changing. This t is your tangent vector is changing with respect to arc length, not time, not angles, arc length. And that is essentially the original formula here. So what we're talking about here is, suppose you have some kind of curve in space. The tangent vectors aren't changing so much right here, but they are changing a lot starting like right here. They're changing quickly. So as you go along a certain little piece of the curve, let's say you're like right here to maybe here, you're seeing how fast those tangent vectors are changing. So in this spot right here, they're changing very quickly, so the curvature would be high. And for example, this spot right here, they're not changing much at all, so the curvature would be smaller. So if you have something that's circular, the curvature K is going to be bigger, so let's call this number 1. Then something like this, let's call this number 2. So curvature of 1 would be greater than the curvature of 2 because the tangent vectors are changing much quicker in 1 than they are in 2. In 2, they look very similar. All right, so that's the curvature. So that's how we talk about curvature in mathematics. And it's just like what you would say, like to someone, a layperson, there's a lot of curvature in this curve, but there's not much curvature in this curve. In fact, there's none here. And if you notice in this line, the tangent vectors are all the same. All the tangent vectors are the same. So for a line, the curvature is 0 because they don't change at all. Now, it's not so simple to find the curvature in terms of the arc length here. This is not a very simple thing to do. So using some theory that I'll let you look at in the book, this is more like what you're going to be using, this one and this one here, these two formulas here. This is very similar here. It's the first one just measures the change in t with respect to the change in it's essentially the change in t with respect to the change in the tangent vector. So, all right, I'll derive it. I'll just derive it because otherwise it's just going to be confusing. Okay, so remember t is our unit tangent vector. Unit tangent vector. Let me blow this up a little bit. Unit tangent vector. Now the change in t with respect to little t, so is going to be same as the change in t with respect to the arc length, and then I can multiply times the change in the arc length with respect to t. This is like s of t, remember s of t, and then if we did the derivative of s of t, that's what we're talking about here. All right, now k is just the length of the, it's the absolute value of how the tangent vectors are changing. Well, if you take the formula before and you just divide by ds dt, so I'm going to take this quantity and divide both sides by it, you're going to get dt over dt, capital T, over dt over ds over dt. So I can replace this with this. So we get magnitude of d capital T with respect to d little t over ds or dt, and then the dt's cancel, but we wouldn't want that to happen because then we would just get back to that. If you look, ds dt is just r prime of t. So the top is just t prime of t, and the bottom is just r prime of t. Look back in the video and you'll see that. So that's how we get this formula here. All right, now with a little bit more ingenuity, you can do this formula as well. All right, so I'll be giving you these formulas on the test. All right, so let's do an example of this. Let's just find the curvature. So let's find, for example, find the curvature of r of t equals, let's do cosine t, sine t, and then just t. This is the helix. Right, so we do r prime of t, which is negative sine t, cosine t, and then 1. And now you do the length of that, which we found to be square root of 2. And now, so therefore, t of t is r prime of t over its length, which is, the length is root 2, so it's 1 over root 2, and then r prime of t is what we have here, so it's negative sine t, cosine t, and then 1. Now we're going to take the length of this, so then t prime of t, I'm sorry, we take the derivative, so it's 1 over root 2. When you take the derivative of a vector function with a number up front, you can just bring the number out in front. So the derivative will be negative cosine t, negative sine t, and then 0. Now we take the length of that. What I'm working toward is, I'm working toward this formula right here. So I'm taking the t and I'm finding its length. Right, the derivative and finding its length. Well, the length of this is just 1. That's cosine squared plus sine squared plus 0 square root. The length is 1. So t prime of t is just 1 over root 2. Okay, now r prime of t was root 2. So what this says is k is the length of t prime of t over the length of r prime of t, which is 1 over root 2 over root 2, which is 1/2 when you do the math. So that is the curvature of the helix of radius 1. Now let's compare that. Let's compare to just a circle. And let's say the circle is cosine t. Let's make r. So r of t is cosine t, sine t, and then let's say it's a circle in the xy plane. So r prime of t is negative sine t, cosine t, and then 0. Now you take the length of that. That'll just be 1, just square root of sine squared plus cosine squared. Okay, so that's 1. Now we're going to take our t then is r prime over the length of r prime. So that would just be the same thing because r prime, the length of r prime is just 1, so it's negative sine t, cosine t, and then 0. And so now we take the derivative of that. Well, that just gives us negative cosine t, negative sine t, and then 0. Now we take the length of that. Gives us 1 again. So apparently, so k equals length prime of t, length of that over length of r prime of t. Well, r prime of t we found to be 1, and then t prime of t we found to be 1. So this is equal to 1 over 1, which is 1. So the circle of radius 1, which is this right here, is a circle of radius 1, has curvature 1, 1. Now, if you take that circle and instead of drawing it in a circle, you pick your pencil up as you go, you pick your pencil up, then there's less curvature there, and that's borne out by the curvature of that helix of radius 1 being 1/2. So in general, what we can say also from all this is, here's a little fact, the curvature of a circle of radius a is 1 over a. So proof maybe on the test, maybe, shouldn't be that hard. You're just going to have r of t is a cos t, a sine t, and then 0, and you'll see it. Just work it out. So what this says is the bigger the circle, the less the curvature. Circle, the less the curvature. Why? Well, let's just compare these. Compare a couple. Let's compare 3 of them. So why? Well, okay, so if the radius is a, then the curvature is 1 over a. So let's compare 3 of them. So if the radius is, so if a versus the curvature, if a is, let's say, 1/10, so a is the radius, then the curvature is 1 over 1/10, so the curvature is 10. If a is 1, we knew the curvature was 1. If a is 10 now, the curvature is 1/10. So if you compare 3 circles, so the outer circle has a radius of 10. This one is radius 10. The next one is radius of 1, and the next one inside is a radius of 1/10. That's the radius. So if you can see that the curvature is much bigger for the very small one than it is this one. This one here, if you zoom in, it almost looks like a line. So the bigger the radius, the smaller the curvature. So here's a little fact. As r goes to infinity, the curvature goes to 0. And if the curvature goes to 0, remember a line has curvature equal to 0. So if you make the circle really, really big, it gets closer and closer to a line. So a circle of infinite radius is a line. So a circle, well, let's just say this, a line is a circle of infinite radius. Now I'm kind of playing around with the math here, but it's basically it. All right, so now next topic is the frame. Actually, it's called a Frame frame, so this is that TNB I was talking about. So we're going to define two new vectors. N is going to be the normal vector, and it's going to be defined as N is the derivative of T, and then divided by its length. And then B is going to be T cross N. Now, since we're using cross product here, it matters where T and N are. So if T is down here and N is here, they're perpendicular, by the way. Then when you do the right-hand rule, let me draw it up here. When you do the right-hand rule, your right hand there, then B is going to be straight up, and it's going to be perpendicular to both of these. So this is B here. So this is the Frame frame. Let me pull over a video, a little animation of this, the Frame frame for different objects. Pull this down. And so this is the first curve. The Frame frame goes around the curve, and it kind of serves as a coordinate system for the curve. So you can pick points on the curve and determine what those points are with respect to T, N, and B. Now let me stop for a second here. If you notice, the tangent vector points in the direction that the curve is being. The tangent vector is in blue. It's this one, the tangent vector. Points in the direction of the curve, and the orange one is the unit normal vector that points in the direction pointing inward for a circle, and then B is the light blue one that's always perpendicular to them. So B for a circle would be 0. You can move this around. So if you look, B is always pointing straight up from the circle. I think there's another way to see it. Maybe it's like this. You can even track it. So as you go, you look, B is going to be pretty much, it's going to be perpendicular to the circle, because T and N, let's stop this for a second. T and N, these two vectors here, will form a plane that the curve, the T and N frame, the plane, pretty much approximate where the curve is the best. So you can do this for different curves as well. This one, I mean, not track it. So the frame goes, TNB frame goes along. So it just forms a little coordinate system as you move along a curve. What's this fourth one? Yeah, this one's kind of cool. You can track it as you go. So that's how it works. So notice how fast, when it's going around a really curved piece of it, high curvature, how fast those tangent vectors change. So watch, as it's going around there, wait, let's see, it's going to go real quick around that. And so we're measuring the curvature by how fast the tangent vectors are changing. Okay, so enough of that. While I'm on these little videos, I'm going to show you what's called the oscillating circle. And that is going to help us out a little bit too. So the oscillating circle is the circle that is 1 over, okay, so let's get this down. So see how this, you have the circle here. See how it approximates the curve a bit. So what it does is the oscillating circle has radius 1 over k. So in other words, if the radius is, so the radius is 1, the oscillating circle has radius, oscillating circle radius also has radius of 1. If the radius is 10, remember the curvature was smaller, then the oscillating circle radius would be 1 over 10. So I'll show you how this works. Let's get rid of this. So let's animate this. So as you move along this curve, this is the first curve, the oscillating circle gets smaller and bigger. So let's stop it right here. So the radius here is small because the curvature is large. As we move along the curve, though, the radius of the oscillating circle gets larger because the curve has less curvature. So the less the curvature, the bigger the circle. Why? Well, because the oscillating circle approximates the curve the best using circles. So if you notice, as you cross over the threshold of the curvature being 0, the curvature being 0 would be the radius of the circle would be 1 over 0, which is infinity. So the radius of the circle right here is almost infinite. And then when you cross that, then the circle crosses over and then it gets much smaller. And if you look, the curvature really, the circle here really approximates the curve very well. So I would invite you to play around with this. This is in the media, of course. There's more of these. That's another one. Yeah, this one's kind of interesting. It's like a little sine curve. So yeah, these circles like this. Okay, so play around with that a little bit. So that's the oscillating circle and the unit normal vector. This is a unit normal vector and a unit binormal vector. All right, so play around with some of the examples in the book. Learn about the oscillating circle and try to read the book and understand this material better.